Hello and welcome back to my channel once again. Today I'll be talking about the acceleration stop distance required, that is ASDR, or in short sometimes it is also known as the acceleration stop distance. In my last class I have talked about the takeoff distance required on a dry runway followed by a takeoff distance required on wet and a contaminated runway. You can find that video on my channel. The topic will be takeoff distance required. So now, as we discussed earlier, that during the takeoff, for the determination of performance of an aircraft, one engine has to fail. The speed at which the engine fails is known as the V engine failure, or in short it is known as the VEF. Right? So we will draw a runway. This is the runway, and the length of the published runway is what we call it as a TORA, TORA, or takeoff run available. So if you have a specially prepared surface which can be used in case of a reject takeoff, that place is what we call it as a stop way. STOP, stop way. Now the total length from the beginning of the runway till the end of this stop way is what we call it as a acceleration stop distance available, or ASDA. For the performance computation of an aircraft, in the event of an engine failure, the captain has got two options, that is either to continue the takeoff or to abandon the takeoff or to reject the takeoff. In case the captain of aircraft decides to reject the takeoff, my aircraft should be able to stop within the ASDA, that is acceleration stop distance required. Now let us consider that an aircraft is lined up here, and at this point is the brake release point. Brake release point. So this is the time the aircraft is going to accelerate, and as we discussed earlier that one engine will fail in propeller aircraft. It is generally the critical engine failure which is considered fail. The speed at which the engine fails, as we have discussed earlier, is VEF. After the engine fails, the captain of the aircraft will take 1 second. It is considered that the captain of the aircraft will take 1 second to recognize and react to the situation. So after engine failure, I will have 1 second to recognize and react, and the speed at which the pilot decides to reject the takeoff in today's class, that reject the takeoff, okay, is what we call it as a V1. At V1, the pilot has decided to reject the takeoff and initiate the actions to reject the takeoff. However, the aircraft will take some time to respond to the actions. That means to say that the aircraft was accelerating with full power in case of a turboprop or full thrust in case of a jet engine. The captain at V1 will put the power lever or the thrust lever to idle, wherein the engine will take some time to spool it down. Okay, that time needs to be considered. Secondly, the pilot needs to apply the brake. Okay, that also will take sometime. There is always an inherent delay from the action which is applied by the captain of the aircraft and the aircraft to react. The reaction time for the aircraft on the captain's action is taken as 2 seconds. After this 2 seconds, the aircraft is considered retarding and will have to come to a complete stop at or before the stopway, that is the acceleration stop distance available. So during this time, aircraft is considered accelerating with 2 engines from the brake release to the V engine failure. At V engine failure, the captain of the aircraft has not done any action because there is a 1 second for him to recognize and initiate the action. So during this 1 second period, the aircraft is still accelerating with the operational engine, and therefore the aircraft will accelerate with 1 engine in case if I am talking about the twin engine aircraft. So for computation of the distance, that is ASDR, acceleration of 1 second will be considered. Thereafter, the captain has initiated the action to reject the takeoff at a V1. However, the aircraft is still taking some time to react onto the captain's action. During these 2 seconds, strictly speaking, my aircraft would have started a retardation. However, in order to be more conservative for calculation, okay, in this 2 seconds, it is considered that the aircraft is still at V1 speed. At the end of 2 seconds, the aircraft will be considered retard, and then come to a complete stop at or before the acceleration stop distance available. The entire distance from the brake release, that is from the brake release till the time the aircraft comes to a complete stop, is what we call it as the ASDR, which I said has to be less than or equal to the ASDA. On a dry runway, this is ASDR on a dry runway, then with 1 engine inoperative. So therefore, this ASDR will be known as the ASDR on a dry runway with 1 engine inoperative, or in short, it can be written as a N-1. Let me draw the runway once again, and we'll consider the acceleration stop distance required on a dry runway with all engines operational. At times, because of certain situations, you may reject the takeoff with all engines operational. So now this is the runway, and let's consider that this is the stopway. Here it is the aircraft is lined up, and this is what is the brake release point. From the brake release point, the aircraft will accelerate till the time it reaches V1 in this case, because we are not considering the engine failure. At V1, the captain of the aircraft initiates the action to reject the takeoff, but as discussed earlier, the aircraft will take 2 seconds to react onto the captain's action, and will retard, and will have to come to a complete stop at or before the ASDA. This distance from the brake release till the time the aircraft comes to a complete stop is the ASDR, acceleration stop distance required on a dry runway with all engines operational. All engines are operational are generally written as N, and with one engine failure is written as n minus 1. Now let us talk about the ASDR on a wet or a contaminated runway. This is the brake release point. The aircraft accelerates with all engines till engine failure, V engine failure, and the pilot will take 1 second to react, and he rejects the takeoff at V1, and the aircraft will take 2 seconds to react to the action and then retard and come to a complete stop. So this distance, as we discussed earlier, was ASDR n minus 1 on a dry runway. If the runway is wet or contaminated, the aircraft will take more time to accelerate, because if it is contaminated with water, the tire which when roll over to this water particle has to displace the water particle which are there under the runway, and a little maybe compressed by the tire. But if the runway is contaminated with snow, most of the snow will be compressed by the tire when roll over, and some of them will be displaced. While doing so, the aircraft is going to lose some amount of energy. So therefore, any loss of energy in an aircraft in its forward motion is what we call it as a drag. So this is known as a displacement drag and a compression drag. Now, when the aircraft wants to stop, needs to apply the brake, because of the reduction in the surface friction, the aircraft will take more time to stop. So therefore, the acceleration stop distance required on a dry runway was this, but the aircraft in this case, when the runway becomes wet, will not be able to stop, and it will stop in this case a little ahead of the stopway, which is not legal. However, this distance is what we are going to be saying that ASDR, okay, n minus 1 on a wet or a contaminated runway. But can I do this? I cannot do this because my aircraft is going to go out of the ASDA. At all times, the ASDR has to be lesser than or equal to the ASDA, irrespective of whether the runway is dry, wet, or contaminated. So therefore, in this case, the aircraft will have to reduce some amount of weight. As we know that more the weight, more the momentum, so the aircraft will take longer period of time to stop. So if I reduce the weight, it will take lesser amount of time to accelerate. At the same time, it will take lesser amount of distance to stop. So now I need to subtract some weight from the initial takeoff weight. So let us say that this is 1000 kgs has been reduced, and then now finally I have come to a complete stop exactly at the end of the ASDA. Now, as we said that, now we have adjusted the ASDR n minus 1 weight so that it is exactly equal to the ASDA. So the distance from the brake release till the time I stop is the ASDR. Now, however, if you recollect that in order to make it feasible for us to stop before the ASDA, okay, I have reduced a large amount of weight, that is 1 ton in this example. Now, the regulators allows the airliner or the operator to use the reversers in case wet and the contaminated runway. So now, in case of a wet or contaminated runway, I am allowed to use the reversers. So with the use of reversers, okay, initially without the reversers and without any reduction in the weight, the aircraft was able to stop here. But now, since I am allowed to use the reversers, my aircraft will be able to stop, let's say, somewhere here with the use of reversers. This distance from the brake release till the aircraft come to a complete stop with using the reversers is the ASDR on a wet or contaminated runway with one engine failure. ASDR on a N-1 on a wet stroke contaminated runway. So now if you have a look at this, I am able to stop beyond the ASDA. But however, the distance by which I have overshot the runway has become lesser. So in this case, the airline or the operator will have to reduce a lesser amount of weight, that is, example, 200 kgs, so that it brings the acceleration stop distance required equal to the acceleration stop distance available. So now if we have to define the acceleration stop distance required on a wet or contaminated runway, it is that distance from the brake release till the time the aircraft comes to a complete stop by using the credit for the reversers. So this is the final ASDR N-1 on a wet or contaminated runway. Now let us assume the second condition, that is the aircraft rejected at V1 and because of the use of the reversers, the aircraft is able to stop here. Stop here. In this case, I still have some distance left. Theoretically speaking, this leftover distance can be converted into a weight so that you can put additional 100 kgs of weight, for example. But the regulators does not allow you to do so. Because of the use of the reversers, if your ASDR on a wet or contaminated runway becomes lesser than the available distance, you cannot convert it into the weight. So if we have a look at that ASDR on a dry runway or a wet runway, so in case if the airline is allowed to convert this leftover distance into the weight, it would have exceeded the weight of on a dry runway, which is not allowed. So therefore, if you are doing it manually, calculating manually, I need to calculate the weight on a dry runway, considering the ASDR, and the weight on a wet or contaminated runway, considering the acceleration stop distance required, and go by the lower of the two figure. This process is again known as a dry check. If you remember, we did the dry check in the continuation of takeoff by comparing the TODR with the TODA after having used the benefit for the reduction of screen height to 15 feet. So now this dry check is for the condition considering the reject takeoff. So that's all about it for today. Thank you, ladies and gentlemen.